So this is exactly what I was talking about. The very first term today is conjecture. A conjecture is an unproven statement based on observations, okay? And that is essentially what we just talked about up here. If I said angle B is a right angle, okay, as of right now, that would be a false statement. You can't just look at a picture and immediately say that's a right angle without knowing some information, okay? So that is what we do when we make a conjecture. Proving it is what we have to be able to do. We have to have some information to be able to prove that that is indeed a right angle, okay? And right now we don't know that. So that's why we'd have to say that's a false statement. Okay, inductive reasoning. What we're going to be doing a lot today, and you've done this before, but you're going to be finding specific patterns, sequences, and you're going to continue them on, okay? So we're going to look at some examples of each one of those. And then you're going to write a conjecture or statement that tells why we know what we're doing, okay? And so if it's like a list of numbers, are we adding something each time? Are we subtracting something each time? If it's a picture, what are we doing to the picture each time, okay? So sometimes these are a little bit tricky because you're looking at, you know there's some type of pattern because it'll tell you there's a pattern and you got to figure out what it is, okay? Let me show you an example before we get into some of those examples. Okay, so here we have a sequence, 20, 19, 17, 14, 10, okay? And a couple things I would tell you here to kind of look at. If the numbers are going down, usually there's two things that could be happening. Either going down means we're either probably going to use subtraction or we're going to use division. If the numbers are going up, we're probably going to use addition or multiplication, okay? So these numbers are definitely going down. So we want to try some different things. And so the first thing that we would look at here, to go from 20 to 19, we go down 1. To go from 19 to 17, we go down 2. And then we go down 3. And then we go down 4. Okay, is there a pattern forming? Yeah, okay. So a conjecture in this case is going to be we're going to subtract one more number each time, okay? Therefore, the next time I'm going to subtract would be what? Minus 5, okay? And that puts us at 5. And then once the next two terms in the sequence, so 5 would be the next term, and then what am I going to subtract next? Okay, we're going to subtract 6. 5 minus 6, -1, okay? Don't freak out if we get into the negatives. It's okay. Negatives are a number just like positive numbers, right? And sometimes we freak out like, hey, we can't be in the negatives. Well, no, why not, right? We can be negative. It's okay. Okay, the next one gives us a picture. There's a pattern going on. Describe how to sketch the fourth figure in the pattern and then sketch the figure. Okay, any ideas? Yeah, Hannah?
Add one more line evenly spaced with the other lines.
Okay. Okay. So we're going to, here we evenly cut it with one line. We take a piece of pizza and we just cut it in half, right? And then we cut it 2 ways, but we cut it evenly. And then we cut it 3 different ways, evenly once again. So we're going to cut by 4 lines evenly. So that's going to go 1, 2, and then we're going to cut it just like most pizzas or pies would be cut. We're going to go diagonally, and we have 4 lines. Okay, so we cut it in half and half, quarters and quarters. And how many pieces do we have? 8. Okay, and they're shading in just one of the pieces. So we'll just shade one of them in to make it the same as the others. Okay, another way that some people might look at this is 2, 4, 6, 8. So the number of pieces that we're cutting is going up by 2. Okay, and so could there be more than one correct answer on some of these? Yeah, possibly, right? And here's another way you could look at it. Figure 1, figure 2, figure 3, figure 4. This is the number of the figure. Figure 1 has 2 pieces. Figure 2 has 4. 3 has 6. 4 has 8. How is 6 related to 3 and 8 related to 4? Multiply by 2, right? So there's 3 different ways that I've basically made a conjecture about what's happening. None of those are wrong. None of them are more right than the others. It's just different ways that I could describe what's happening. Okay? Not all of them are going to have multiple ways of doing it, but just trying to show you that sometimes, some people see it differently, and it's okay. That's kind of what makes all of us a little bit different. Okay. SRQP is my pattern. Find the next, let's go the next 2 letters in this pattern. Good, absolutely. Okay. It's the alphabet backwards. Okay, what comes before P? O. And what comes before O? N. Okay. And I could keep going if I need to, but those would be the next 2 in this sequence. Alphabet going backwards. Okay, so just a couple of different variations of different types of patterns or sequences that we could see, and just trying to continue that pattern as we go. We have some vocab here because these are some words that you're going to see on some of our examples, or especially on Big Ideas today. And these are some of the things, we haven't talked about some of these things for a while, especially the types of numbers. The numbers over, or the vocab words over here are your operations. Okay, those should hopefully look pretty familiar to you. When we talk about sum, what do we talk about? Addition, right? That's the answer to an addition problem. Difference would be subtraction. Product, multiplication. And then quotient's the 4th one, which would be division. Okay, we'll show you some examples here in just a second where we use some of those words, maybe not all of them, and talk about a pattern. Okay, types of numbers. We haven't talked about types of numbers for quite a while. When we talk about natural numbers, what numbers are natural numbers? Where do they start? What numbers are we talking about? Anybody remember? What do you think, Adrian? Not sure.
Are natural numbers like non-negative numbers?
They're non-negative. Okay, that's good. Okay. So what about like 2.5? Would that be okay? Do we want fractions? Do we want decimals? No? Okay. What about 0? Do we want 0? Because 0 is non-negative. Should we include 0 in our set here? So your natural numbers are the way that you naturally started counting, is the way I remember it, okay? You probably, maybe you started with 0, but it's our counting numbers, right? So 1, 2, 3, and on up. Okay, whole is very, very similar, but here's kind of how I remember whole. It has an O in it, and I kind of remember whole as adding a 0 to my set. So whole numbers start at 0 and work their way up. That's the only difference. Okay, what about integers? Anybody think they know what an integer is? Yeah.
It's a number that's like not a decimal or fraction. It could be negative or positive.
Okay, good. And so it's our counting numbers with negatives added to it. Good. So we're going to add negatives to our list. And we're going to keep going. The dots mean we're going to keep going. In this case, we're keep going both ways, both going to the left and to the right. Okay, and then maybe the hardest of all of them is rational. So a real number is any number, okay? We don't have that on the list here. A real number is any number. You name me a number, it's a real number, okay? But rational is a smaller set of that. What makes a number rational? So let me ask you this. Would 3 be a rational number? Can a number be part of more than one set? 3, 3, 3. So can a number be part of more than one set? Okay. So do you think 3 would be rational?
Rational numbers that divide evenly.
Not necessarily. But you're on the right track. You're thinking correctly. Okay. It could divide evenly. Like, for instance, if I said 8 over 2, okay, which makes 4, which would really be a natural number, a whole number, and an integer also, okay? But it's also rational, okay? What if I did 8 over 3? Rational or not rational? Any ideas? Any thoughts? You guys remember? Have you ever heard the word rational before?
I forgot.
You forgot, but you've heard it maybe? Yeah? Okay. 8/3 is a rational number. Okay. What about 1/2? Yep. Okay. So a rational number is any number you can write as a fraction. 4 doesn't typically get written as a fraction, right? But could we express it as a fraction? 8 over 2? Yeah. And typically we don't do that. Or I could even say 4 over 1. Are there any numbers in our numbers that we know that are not rational? What if I did 0 over 5? That'd be okay. I think we just had one on our test last week. We had a number that was not rational on our test. Anybody think about what that was? Yeah. It was, you're on the right track, yes. The square root of 29. Yeah. Because what happens when I took the square root of 29? What kind of number did it give me? A decimal. And what happened to that decimal? That decimal goes on and on and on and on. Okay? I cannot express that as a fraction. So if it's repeating like 1/3 or 0.3 repeating, I can write it as a fraction. Okay. Another one. These are examples of not. Another one that is not is pi. You guys see pi before? Yeah? What do we know about pi?
It's infinite.
It's infinite, right? It goes on forever. It keeps going and going and going and going. Okay? So any number that goes on forever that does not repeat is, we call it irrational. I know that's not a number we had on our list right here, but that's called an irrational number. Okay? So just, we haven't done some of that for a little while. Three random letters.
I think the next two would be or the next like 5, or however many, T, F, S, S.
Okay, how come?
Because M, T, W corresponds to Monday, Tuesday, Wednesday, so it could
There
be
it
the
is.
days of the week.
Yeah, so it's a pattern, right? There's a pattern. We could continue that pattern on, but sometimes it's not just popping out to me. Maybe there's not any math involved. So here my conjecture would be the first letter of the days of the week. And then we could continue that pattern. But that's an example of a conjecture, right? And sometimes that's kind of hard to come up with because we're thinking outside the box or we're thinking mathematically. And sometimes it may not have any mathematic need at all. It's just a pattern, something that we're pretty familiar with. We know the days of the week, but it may not be the first thing that pops in our head. All right, consecutive integers. When I see or hear the word consecutive, what are we thinking about? Continuous, right? And so another way you might think about it is like back to back or in a row. So if we had consecutive integers, here's that word integer. That's why we're kind of introducing you to the types of numbers again, because we're going to see integers. We haven't seen them for a while, so that's why we kind of put them on the beginning of the notes here. So we're talking about our counting numbers, 2, 3, 4, 5. Could be -2, -3, -4, -5. So 3 consecutive integers, like 3, 4, and 5. Make and test a conjecture about the sum of any 3 consecutive integers. Okay? So what we need to do is we just need to make up an example, right? So 3 consecutive integers. The example they gave me was 3, 4, and 5. And we see the word sum here, okay? The sum of those 3. If I add those 3 together, 3 plus 4 is 7. 7 plus 5 is 12. Okay, is that enough to make a conjecture off of? Just one number? One example? No, okay? I could say all kinds of things about that, but we need to have a little bit more data, right? So give me 3 other numbers in a row. 6, 7, 8. Okay, let's try that. 6 plus 7 plus 8. 6 plus 7 is 13. 13 plus 8 is 21. Okay. Anybody getting a vibe for a conjecture yet? Anybody want to take a guess on a conjecture?
I have a guess, but I'm testing it first.
Okay, good. Let's do 3 more. 10, 11, 12. Okay, and I'm just picking, you can use any 3 consecutive integers you want. I'm just picking 3 random ones, right? So if you're wondering where am I getting my numbers, if we add these together, we get 33. So we need to look at a couple of examples. Now we got to come up with a conjecture. And we got to come up with something that is happening on all 3 of these, and it has to work for all 3. Now you can keep coming up with more examples if you want to, but right here we have 3 examples, and we have to come up with something that is true about all 3 of these. Yeah? They can all divide by 3. Okay, that's good. I like that. 12 divided by 3, 21 divides by 3, and 33 divides by 3. Okay, a little bit more. Okay, that is a true conjecture. Okay,
All of them have at least one number that can divide the sum evenly.
okay. Like the same number or a different number?
What?
So say it again. All of them have at least one number.
All of the sets of consecutive integers, when you add them together, the sum can be divided evenly by one of the integers used to make it.
Okay. Yeah. You're up. Yep. You're on the
They
right.
can all be turned into 3 by dividing them by the middle number.
There you go. There it is. Okay. You guys are all kind of working together to get there, right? If I said, what if I go from 4 to 12, what am I doing? Multiplying by 3. If I said I'm going to take the middle number and get to 21. If I said I'm going to take the middle number and get to 33. Okay? So, the middle number multiplied by 3 gives the sum. And you could come up with another example to see if that truly does work again, but that is the rule. A little bit tricky to come up with though, right? So you just have to kind of, and like, is it a wrong conjecture to say they all divide by 3? No, okay? But typically what I would say is that these 3 have some type of relationship to get to here. So we're trying to kind of connect those together. How do those 3 numbers connect to get to that sum? And so there could be lots of possibilities in some cases, but try to come up with the one that's the most specific. Okay? May contest a conjecture about the sign of the product of any 3 consecutive, or not consecutive, but 3 negative integers. Okay? So let's go -4 times -2 times -1. What's -4 times -2? 8. 8 times -1? -8. Okay, let's do 3 other ones. -7 times -3 times -2. The numbers that I use don't really matter as long as they're all negative. -7 times -3? 21. 21 times -2? -42. Okay, any guesses right now?
The product will always be negative.
The product will always be negative. Good. Because what happens when I multiply the first 2 together? Makes a positive. And when I take a positive times the last one, it turns it negative. Okay. So the product will always be negative. Okay, the last group of things here. A counterexample. We have a conjecture, and we're going to find one thing that makes it false. There may be more than one thing, but we're going to find one thing that makes it false. Anything that makes it false is called a counterexample. In football, we have a play called the counter, right? We run a play called 46 counter. And what we do is we fake it one way, and the ball ends up going the other way, right? So we try to fake the defense out. Make them think it's going here when really it's going over here, okay? And that's what we're doing here, is we're trying to find something and makes it false, or makes it does not work. So they give us a statement here. The sum of 2 numbers is always more than the greater number. Okay, the sum of 2 numbers is always more than the bigger number. Okay, so if I did, let's go with 4 plus 5. I get 9. Is 9 bigger than 5? Yes. Okay, so is that a counterexample? No, because that proves exactly what we said, right? 9 is bigger than 5, so this is not a counterexample. That does not prove it false. We're looking for something that proves it false. Okay, what do you think, Hannah?
4 plus negative 3 equals 1.
Okay. Is 1 bigger than 4? There it is. There's a counterexample. So what's the key? What do you have to use here? A negative, okay? What else could I use? There's another number you could use too. 0, yeah. 6 plus 0 is 6. Is 6 bigger than 6? No. Okay, so there's 2 examples of a counterexample. Any negative or 0 would work for a counterexample here with your addition. Okay, you only have to come up with 1, but no, there's a lot of possibilities. The value of x squared is always greater than the value of x. Okay, so let's say x is 3. 3 squared is 9. Is 9 bigger than 3? Yep. So that one supports the statement. That one is not a counterexample. Okay? So, what would be a counterexample? Any ideas? Could I do a negative? Negative is always kind of a fun one to go to. Let's say x is negative 4. What if I do negative 4 squared? It's positive, okay. Is 16 bigger than negative 4? Yep. So is that a counterexample? Nope, doesn't work, okay. What else could I try? 0, okay. We could do 8 is my x. Oops, sorry, 0 is my x, not 8. X equals 0. What happens if I do 0 squared? 0. Is 0 bigger than 0? No. So there's a good counterexample. Okay, any other ideas what I could use here? There's another possibility. Quite a few other possibilities. Okay, 1. Yep. X equals 1. 1 squared is 1. Okay, that would be a good one. Okay, or you could do a half, a fraction. Okay, and if I were to square a half, I would get a fourth. A fourth is less than a half. Okay? So that would be another counterexample. So there, I gave you 3 of them. So that's just showing you there could be a lot of possibilities. There's not just one answer that has to be it. And that's kind of what we're looking for. Okay, finally, all numbers that end in 8 are divisible by 8. Okay, so let's start with 8 divided by 8 is 1. Okay, the next number that ends in 8 is 18. Does 18 divided by 8 give me a nice whole number? No. That's what it means to be divisible. It divides out evenly to be an integer, not a decimal or a fraction. So 18 would be a counterexample. What about 28? Yeah. What about 38? Yep. What about 48? What's 48 divided by 8? 6. Okay. And 6 is not a decimal. So 48 would not be a counterexample. But 18, 28, 38 would all be counterexamples. So lots of possibilities on a lot of those. Trying to find something that makes it false.